Okay, welcome to video 1 of our lecture series from Monday, April 10th. This is our warm-up where we look at kind of our first practice and foray into applying stoichiometric principles by looking at the difference between a mole quantity from our pantry versus a mole ratio from our balanced chemical reaction. So I've got this example laid out here, and all of this information up here is actually just kind of interesting. So water splitting, or forcing the dissociation of water into its separate components, right? It's H2 and O2 gases. This is not an aqueous process, it's a gaseous reaction, is something that has been considered for a while in green and alternate energy circles as a way of producing kind of carbon and greenhouse gas free energy. Because when you look at this reaction where water decomposes into H2 and O2 gas, this decomposition, this splitting of water, is actually something that releases a bunch of energy. The only reason that it hasn't been adopted is because it also requires a lot of energy, so it's kind of inefficient. But people are thinking about ways where we could maybe make the decomposition a little bit more efficient so we can harness the heat released from this decomposition to do things like heat steam, which is basically everything we do in our combustion engines, right? So water splitting is a process that's gained interest as the forced decomposition of water releases large quantities of thermal energy, and I've shown you the decomposition reaction here. So anytime you're given a chemical reaction and you know that you're going to do something with it, you should always, always, always start by checking that your chemical reaction itself is balanced. So let's look at this decomposition of water and ensure that we are balanced. So on my reactant side, I have 2 hydrogen atoms, and on my product side, I have 2 hydrogen atoms. So far, so good. And then on my reactant side, I have 1 oxygen atom. However, on my product side, I have 2 oxygen atoms. So I need to double the amount of oxygen that I have on my reactant side, and I'm going to do so by doubling the amount of water that is decomposed. So now I'm decomposing 2 molecules of water. Now, in doubling the amount of water that has decomposed, I have not just affected my amount of oxygen, but I've also affected my amount of hydrogen. So where 1 molecule contained 2 atoms of hydrogen, 2 molecules will give me 4 total atoms of hydrogen. And on my product side, I've yet to have 4, I only have 2. So I need to then double the amount of H2 that's made. So again, anytime that you are balancing a chemical reaction, you are of course getting a molecular ratio, but remember, number of molecules and number of moles are related by a constant, Avogadro's number. So anytime we get these coefficients from balancing a chemical reaction, we are obtaining mole ratios that exist between reacting species. And this is what I call our recipe. This tells us how much of one thing is needed to react in proportion with another thing in order for the reaction to complete. So if I wanted to decompose water, this would only happen if 2 molecules of water decompose into 2 molecules of hydrogen gas and 1 molecule of oxygen gas. All right. So now that we have our recipe, tells us the mole ratios that are needed in order for this reaction to proceed. Let's look at an example where we are now rifling through the pantry. We are going to look at some actual amount of either reactant or product that is either used or made. And then we are going to see if we can't use some information about that mole quantity and what we found as our mole ratio from balancing our chemical reaction to get some kind of quantitative information about what's going on in this reaction. So A says if 1 mole of H2O is split, then how many moles of H2 and O2 are made? So there's 2 ways to kind of do this. The first way is by using your intuition, right? So remember, we are talking about moles. We are no longer talking about molecules, because anytime we look at our subscripts in a chemical formula as well as our coefficients in our balanced chemical equations, we have scaled everything up to the mole quantity because that is what we use in the lab. So let's look first at our intuition. So what might our intuition tell us about how 1 mole, or having the amount of H2O, would affect the amount of product? So this is thinking about, oh, if I were to go and try to make my scrambled egg recipe and found that in my pantry I actually only had half as many eggs as I had wanted, then it makes sense that I would only be able to make half as much of my product or my overall scrambled egg dish. So since I start with half the number of moles that are given in our coefficient, meaning I start with half of what I have in my pantry compared to what my recipe calls for, then I can only make half the quantity of products. So half of 2 moles would be 1.00 moles of H2 made, and then half of 1 mole would be 0.5 moles. And again, these are not molecules, it's moles, so it's okay that I have this fractional quantity. And again, this is just using what we know about the relationship between our actual quantity and our ratio, where our actual quantity is half as much as our ratio. So that's our intuition. Now let's see if we can't prove our intuition by actually performing a calculation. Nope. Just move all this stuff down out of our way. If Notability will let me, let's see if she's a gracious God today. Ooh. There we go. All right. So the second way that we could prove this is we can prove quantitatively, meaning we can calculate. So let's perform some kind of dimensional analysis, which is, again, our way of talking about unit conversions. So I have to start 1.00 moles of H2O that's decomposing. And let's look at my question here. I want moles of both products, so I'm going to need to convert this starting quantity of H2O into some number of moles of oxygen and some number of moles hydrogen. And I'm going to switch the order. Let's do hydrogen first, and then oxygen second. All right. So this is what we have in our pantry, right? We have only 1 mole of each. And now I am going to use the mole ratio given in my recipe to put us out of the mole of reactant unit and into our mole of desired product unit. Okay, so again, we need to look at our ratio, our recipe. So our recipe says that for every 2 moles of water decomposed, so I'm going to put 2 moles of water in the denominator, I generate 2 moles of hydrogen gas. So 2 over 2 is 1. Notice that my units here cancel. Moles H2O, moles H2O, leaving me with moles H2. And this now gives me 1.00 moles of H2. Does this match our intuition? Our intuition said we had half as much reactant, so we should make half as much product. And the only way we could say that is because we were in a 1-to-1 ratio between this reactant and that particular product. So that makes sense. Yay. Let's do the same for our oxygen. So again, for every 2 moles of water reacted, let's go back to our recipe. For every 2 moles of water reacted, I generate only 1 molecule or mole of oxygen gas, meaning that I need to cut my moles of water in half. So this is saying times 1/2 or divide by 2, 0.500 moles of oxygen. Does this match our intuition? Yes, it does. Okay, let's see if we can't apply this to another example. So same reaction, same recipe. Now we just got a different pantry. So if 6 moles of water is split, how many moles of products are made? So just for our benefit, so I'm not swiping up and down, we know that it took 2 moles of water to decompose into 2 moles of hydrogen gas and 1 mole of oxygen gas. Okay, let's try this with intuition. So I don't have 2 moles of water, rather I have 6 moles of water, meaning I have triple the amount of water to start. So I have 3 times as much H2O decomposing. This means that I should probably have 3 times as much product being formed. So we predict that we should make triple the amount of hydrogen gas, so that is 6.00 moles of hydrogen gas. And triple the amount of oxygen gas, so that is triple times 1, 3.00 moles oxygen gas. And now let's prove that our intuition is rational using our little dimensional analysis. All right, so if I've got 6.00 moles of water, this is my recipe, right? This is what I'm starting with. It's what I actually have available to react. And I know from my recipe that for every 2 moles of water reacted, I generate 2 moles of hydrogen gas. Then 6 times 2 over 2 is going to give me 6.00 moles H2, not H2O, H2. And what do you know? Turns out we're rational people. Yay! Now, what if we were to do the same about 6.00 moles of water decomposing and figuring out now rather oxygen that is being formed? So I have to look to my recipe, which again says that for every 2 moles of water decomposed, I will make only 1 mole of oxygen. So I take 6 moles of water, 6 moles of water, divide by 2, that gives me 3 moles of oxygen gas. What do you know? Yay. Okay. Chew on that for a minute. I'm going to split this video up into two because if you'll notice in parts A and B of this problem, I gave us kind of some softball quantities, right? Like when I looked at 1 mole of water decomposing, I know the relationship between 1 and 2 and 1 and 1, right? This is like a nice, easy, half as much kind of ratio. Same deal with 6, right? 6 is a whole number, so I can relate that to my whole number coefficients by recognizing this triple as much. In our next part of this warm-up, we're going to look at like something closer to what we'll see in reality, which is what if I've got some non-whole number amount of moles, or something that I can't at least figure out intuitively what that proportionality might be. So I'll see you in the next part of this warm-up, and then we will continue on to discussions of limiting reactants.